This video is going to review mechanical advantage. When we look at a machine, we use machines because it makes doing work easier. And one of the ways that we look at how machines do their work is how much it's going to decrease the effort of it to put into doing a task. Now, the thing to think about is that machines do not decrease the overall amount of work to be done. So let's look at this in more detail. So here's the equation for work into a machine and work out of a machine. We have to be concerned with the force that's going to go into a machine and the distance into the machine, and that'll be equal to the force out and distance out. And that helps us to figure out the mechanical advantage. Because if you have a small force going into a machine, then the force out would be very much greater if the distance out was very small. So we'll look at that in some examples in the next few slides. But the equation for a mechanical advantage is looking at the force in terms of effort going into the machine. The force in is going to be in the denominator, and the force output is going to be in the numerator, and that's going to be determining our mechanical advantage, also known as MA. So let's look at some examples. This is the car jack picture that is found on page 132 of the textbook. Now, if we're looking at the work in and work out of the jack, right? So if we see here, the work in, this is your input. So if you were operating the jack, this would be the force in. And the distance down is quite larger. That's the distance in. And the distance that the jack moves is very small. So this is distance out. And this force applying on the car is quite great. This is force out. So if we're thinking about the mechanical advantage of a jack, the force out is very, very high, and the force in is very low. So you can imagine this having a very high mechanical advantage. And really, a mechanical advantage is just the ratio of in to out. So one of the things that we're thinking about when we're looking at a machine is that there's a payoff between having a larger distance and reducing the amount of force that you would need. So if you look on this picture with the girl pushing the chair up the ramp, there is a huge distance that must be covered. So it has a very high distance input, but the output is quite smaller. Now it makes it this person pushing have to have a very small force in because it's less of a grade than if you were just trying to lift the chair right into the truck. So that's the importance of using an inclined plane or a ramp. So if we're thinking about a mechanical advantage here, the mechanical advantage of the ramp would be that the force in is a lot less than the force out if you didn't use the ramp. Again, here looking at the hammer, you can think about the higher amount of force that you have to put into the hammer, right? So the actual arm of the force in is quite low compared to the force being applied to the nail. Now, again, if you think about distance, there's a great distance here for the arm has to move, and the distance that the nail is going to move is quite small, right? Just that small amount of distance that the nail move. That's because all the force is being applied to the nail to make it move. Now, this is the blind picture that's found on page 136 of the textbook. And one thing to think about when we look at the blind is that essentially it's a pulley system. And when you pull down on the pulley, you're going to put the same amount of force down as you put into going into the blind itself. So if, let's say you're using 50 newtons of force to pull up, so this would be so this would be force in over force out. Right? This mechanical advantage of using the blind is actually 1. There is actually no mechanical advantage to using the blind other than it's changing its direction. Right? You pull down and the blinds go up. So some machines could have a great mechanical advantage and some may not, such as the blind example here. So let's look at some examples of calculating mechanical advantage. All right, in this example, we're going to use the mechanical advantage equation. So here we have a box that's going to be pushed up an inclined plane. It's 12 meters long and 3 meters high, and it requires 4 newtons of force to move the box. Um, the force is going to be applied to the box because it's change in distance is going to be 16 newtons. So to apply our mechanical advantage equation, ma is equal to the force out divided by force in. So we're going to take the force out, which is 16 newtons, and we're going to divide it by 4 newtons. And what we end up with is canceling out our units. It's just a ratio. 16 to 4 is 4. So the mechanical advantage of using this inclined plane, because we know the force in and we know the force out, plug that into our equation, and we find that the solution is 4. Now this makes sense because we're not changing the overall work. What we are doing is making it easier for us because instead of making the 3-meter high jump all at once, we're doing it over the entire inclined plane. So the force is greater at the end for only a little bit of force as an input. So let's look at another example. In this example, we have a pulley system, and we're going to look at the mechanical advantage here, and we can see that weight is being applied to our pulley. It is attached here on the pulley system, so you can imagine that the line will actually make this whole unit move up until it hits the bottom of the top pulley. So the string is actually going to go from here through the pulley out as you pull it coming out here. So way more distance coming out on this side. So this is the distance out, and distance in is here. Oops, I have that backwards, don't I? So we got distance in and distance out. There we go. So for calculating the mechanical advantage, we need to know the force in and the force out. So the force into the pulley, this would be the person pulling on the string, would be 25 newtons. And the weight itself is 50 newtons due to gravity. So the mechanical advantage, using our equation, we're going to take the force out and divided by the force in. And that's going to be equal to 50 newtons divided by 25 newtons. And the mechanical advantage, we'll find out, is equal to 2. Remember, our units cancel out. Now, why is it 2? Well, if you look at a pulley system, right, this weight is actually being supported by 2 lines. So each line holds 1/2 of its weight. So 1/2 of its weight here is 25. So this string on the left holds 25 newtons, and this string here holds 25 newtons. So when you add them together, it equals total weight. So you can imagine if we had 3 strings, right, it would be divided by 3. If you had 4 strings, it would be divided by 4. So that's the mechanical advantage of a pulley.